If you're having trouble finding a place. It's just like class. None of the students want to sit in the front row. Okay, well, welcome. Good evening. I'm Doug Arnold. I'm the director of the Institute for Mathematics and its Applications, which is the host of the Math Matters public lecture series. Glad to see many of you back again, and maybe some new faces here. I'm very pleased that today we'll have Professor Chris Budd from the University of Bath in England, who's going to talk about making sense of a complex world. Chris got his doctorate in mathematics from Oxford University in 1986. He's a professor of applied mathematics at Bath, and he also holds the position of the chair of mathematics at the Royal Institute. The Royal Institute in Britain is one of the oldest bodies devoted to the popularization and the dissemination of scientific results. It was founded by Henry Cavendish and Michael Faraday. Chris is the director of two centers at Bath, the Center for Nonlinear Mechanics and the Bath Institute for Complex Systems. He works in a variety of fields of applied mathematics, scientific computation, dynamical systems, partial differential equations, and all sorts of mathematical modeling relevant to problems, especially arising from industrial applications. But Chris might be best known for the really remarkable work he does in the dissemination of science, the popularization of science, and the engaging of high school students and even primary school students into mathematical subjects. He does some remarkable things. He runs a sequence of weekly master classes, activities with groups of around 50 high school students. And in fact, you can read about that because he has co-authored a book. It's called Mathematics Galore. On these master classes, they talk about things like the mathematics of folk dancing, the mathematics behind sundials, African art patterns, all sorts of great stuff. He's disseminated through many other things. He's made videos and DVDs. He even consults with the British Parliament. So there was a person in the National Teachers Union in Britain who said, we don't need to teach the quadratic equation anymore. It's pretty hard and sort of boring. And somebody in the British Parliament got upset on this and held some hearings on whether you did need to teach the quadratic equation or not. And Chris was consulted and ended up writing an article called 101 Uses of the Quadratic Equation, which you can download. It's very convincing, and it was discussed widely in the House of Commons. And he's going back next month. They want to discuss with him further what math is good for, and I'm sure he can tell him. He's somebody who, sort of like, I'm sort of in the same group. I see math everywhere and contributing to almost every problem we see in the natural world, in the man-made world. He's written and spoken about math and criminology, all sorts of stuff. And tonight we're delighted to hear him speak about using mathematics to make sense of a complex world.
Well, thank you. Well, it's very nice to be here. This is my second trip to Minnesota. I'm afraid my first trip was 20 years ago, and it's been far too long for me to come again. But I did consult Doug before I came, and he said, bring special winter gear, so I did. So I'm glad that it's snowing, so I didn't bring it in vain. Anyway, I'm going to tell you today a bit about complexity. And I'm director, as Doug said, of the Bath Institute for Complex Systems, which tries to make some sort of sense of complexity. I think it's obvious, if you look around, that there's lots and lots of things in nature which are very, very complex. I have teenage children, I know. Okay. With apologies to all the teenagers in the audience. And much of the natural world that we see around us is very, very complicated. It's very complex. It's very hard to understand. And what I've got here is a picture. This keeps me awake at nights, this picture, because one of the things I'm interested in doing is studying the way pollution gets transported underground. If there's some sort of spillage of oil, how does that pollution get transported? And that's a picture of what rocks look like over a distance of some miles, and that's a picture of the way the type of rock changes. And somehow we have to make some sort of sense as to how pollution can go through that mess. And that really keeps me awake at night, trying to puzzle my way through that. And what I want to do today is to tell you about all the sorts of examples in nature where things like this arise very naturally, and then how we can try to make sense of it and how we can understand it and actually do something useful as a result. So that's rocks. Let's show some other examples of complexity. Well, here's the weather. Some of you may not realize this. I got a rather worrying shock this morning when I looked onto the internet to see that England had been hit by a hurricane, and had to ring my wife up, and she said, no, it's all right, we're quite safe, but we do need to buy some new windows. So there's a hurricane, and and I think we all know that the weather is a very good example of something that's very hard to predict. Yes, we know it's going to be cold in Minneapolis during the winter, but we can't easily say what the weather's going to do from day to day. And the reason the weather is very hard to predict is that there's lots of things that go to make the weather up, and they all interact with each other in very complicated ways. In the UK, the weather can change very rapidly over very short intervals of time. So that's the weather on the large scale. That's weather on very small scale. That's a cloud. And you can see, just looking at the cloud, why it's going to be hard to predict the weather. You can see there's lots and lots of fine structure in that thing there. And that's inherently hard to predict and very difficult to work with. Here's a rather larger scale version of what happens in the weather. Even if we can, say, predict the weather tomorrow or into a week, no computer that I know of can predict the weather further than a week into the future. And yet that's very important if we want to make predictions of climate. And this is a record of the temperature in the southern Pacific, and you can see that it varies up and down in what looks like a random and very complicated way. And this is the El Niño phenomenon, and the El Niño phenomenon, as I'm sure you're very well aware, can cause enormous changes to the local climate and therefore enormous changes to the productivity of agriculture and fishing and things like that. So many, many people's lives depend on the values in that graph. But I ask any of you if you think you can predict when the next peak's going to be. If you could, you'd make a lot of people very happy. Okay, so there we have the weather. And I'll come back to the weather at the end of this talk, because it's something I'm very interested in, and we'll see how what we can learn about complexity actually allows us to do some work on understanding how the weather behaves. Here's some other examples of kind of complexity in other types of nature. Flocking is a beautiful example of a system where you have lots of individual agents. In this case, these are starlings. And the starlings communicate with each other mostly by visual clues, but also by the way they influence the air currents. And you get beautiful patterns of flocking. I'm sure some of you might have seen this. One of the earliest examples of complexity in nature that was kind of formally recognized and looked at was turbulence. And turbulence is what you get when you take some water, for example, and you pour it into a bathtub and swirl it around. You get very, very complicated patterns. And this beautiful picture was actually painted or sketched by Leonardo da Vinci. Leonardo da Vinci, as well as, of course, being involved with the Holy Grail and all that sort of stuff, was a very, very good scientist, and he studied turbulence. And interestingly enough, some of his ideas are still used a lot in, for example, understanding how blood behaves in the heart. But look how complicated. He's really got that beautifully drawn. This is geology is something I'm particularly interested in. One part of my own scientific research is working with geologists. And when I was at school, I was taught that when rocks buckle, they buckle in nice kind of regular sinusoidal patterns. And I used to believe that until I actually went and looked at some rocks. And if you actually look at them, they're not nice and easy. They are very, very complicated. And again, it's very hard to decide whether we can make any predictions about that. But again, I'll show you how we can make some headway a bit later on. But rocks are really good fun. These rocks are from Cornwall, which is quite near Bath. Oh, seem to have lost one of my pictures there. Not sure what's happened there. I hope I haven't lost any more. We'll see. I'm a bit worried there. Oh, there it is. Computers. Very complex things. So, here are a couple of examples of problems we're actually rather interested in Bath. Complexity isn't something which just arises in nature. Complexity is something which is quite often engineered into structures and increasingly becomes important in the design of modern products. These objects here, these are wonderful things. These are photonic crystals. And a photonic crystal is, I think, holds the world record for the longest, thinnest thing there is. Because what a photonic crystal is a very small and narrow fibre optic cable. It's at most 1 millimetre across, but it's about 10 kilometres long. Incredibly long, thin things, and yet it gets even more complicated than that because these things have lots and lots of little holes drilled in them. And you think, why have they got lots of little holes drilled in them? That looks a very complicated thing, but in fact, it's done for a very good reason. It's done for reasons that, for interesting mathematical reasons, drilling lots of holes in a crystal makes it very, very hard for light to escape. And because light can't escape through them, the light can only go along the cable, and that means they can transmit light for many, many, many kilometres without any energy loss whatsoever. And that's a result which was actually first predicted by using mathematics, and now is an important part of telecommunications. I came here by aeroplane. I'm leaving by aeroplane, and hopefully the aeroplane will work. But aeroplanes are very, very complex things. And this is just part of an aeroplane. This is the undercarriage. And what an undercarriage is lots of bits all jointed together. And when an aeroplane lands, an undercarriage not only acts on its own, but somehow has to cope with all the complexities of the aeroplane, the wings waggling, the fuel tanks, the people standing up before they should do, and stuff like that. And somehow we have to make enough sense of that to be able to predict how to land aircraft safely. And in fact, this one is rather difficult to work with, and you'll see why presently. So here's complexity in engineering. Some of you might have come across things like composite materials, where you deliberately engineer complexity into materials in order to get interesting properties. And last but not least, the most complex thing of all, and certainly in my case the least easy to understand, is human behaviour. Okay, we all know that humans on their own can behave extremely unpredictably. Humans in crowds, well, either they behave even more unpredictably because there's lots of them, or perhaps somehow there's some behaviour which emerges from a crowd because of the way things interact. And that's something which I want to talk a bit about today. Stock markets, that's the UK stock market, as you can see, wiggling all over the place. Can mathematicians make any sense of it? Well, if I could, I wouldn't be here, of course. I'd be earning lots of money somewhere else. But some people think they can. So we've seen lots of examples through what I've shown you of things in nature, things in engineering, things maybe in human behaviour, which look very, very complicated. And the question is this: do we give up? Do we say, life is so complicated, I can never make any sense of it whatsoever, I might as well give up trying now? Or do we say, as scientists, can we make some sort of sense of all this? And maybe by making some sort of sense of it, we can learn how to do better and predict things into the future. So that's the sort of question I want to raise with you today. So, let's get some terms right. What do we mean by complex system? What is a common feature of all the things that we've looked at, from the rocks to the people, to the undercarriage, to these crystals, to, say, starlings in flocks? So what are some common features? Well, here's one. I think we'd all agree that things are complex because generally there's lots of individual components, and those components all have their own behaviour. So in a flock of starlings, you've got all the starlings. Each starling does what a starling does. Okay. But that's only the first thing. There must be, for all the problems we're looking at, some way that these things interact. There must be some coupling between them. And I've used the fancy word here, nonlinear. I direct this thing called the Centre for Nonlinear Mechanics. And what we mean by nonlinear coupling is that when you combine things, what you get isn't just the sum, somehow they influence each other in some way. So that's a nonlinear thing. And thirdly, in many of the things we've looked at, have different scales in space and time. If we look at the weather can change very, very quickly. It can change in a matter of minutes. If a tornado, for example, goes past, I understand that tornadoes are not uncommon in this part of the world. They're increasingly common in the UK due to global warming. Tornado can pass very quickly, but climate can take many, many tens of years to change. Also, a tornado, or you can get very, very small effects in weather, but also weather is something that happens over the whole of the planet. Or, if you're on Jupiter, something even bigger. So, in many, many of the physical systems we look at, wide variations in space, wide variations in time. So that's what I kind of mean by saying nature is complex. That's the sort of things which go on. So there we are. We've seen the weather is an example where we have the components of the air interacting. They interact with the oceans. They interact with the sun. And we all know that CO2 is very important as well. The Earth as a whole, we can think of the whole of the Earth as one big complex system, all kind of the different bits of it all interacting. And other things, disease spread. That's another very good example of something which fits this sort of pattern very well. What happens in disease is you've got agents like humans interacting, you've got viruses which interact with the humans, and also disease is greatly affected by other outside things like pollution in the atmosphere. So all of these are examples of things where you have lots of things going on, these things interact with each other, and you've got all these wide variations both in space and time. So I'm going to stick to that definition. It certainly meets all the examples that I've shown, and we'll see what we can learn from things which have this sort of behavior. This is one of my own favourites example. One of the things that I've studied an awful lot is the human body, not from a kind of medical point of view, but from a mathematician's point of view. And I had this poor PhD student. If any of you, by the way, are interested in doing a PhD, this poor PhD student spent 4 years of his life studying digestion, and in particular poo. Okay, how is that the correct American word? Anyway, it'll be close enough. And we ended up studying a very complex system, which is digestion. And digestion, you have the stomach, which is quite big, the intestine, which is very big, but lots and lots of bits making up the intestine. Although it's very complex, the human body manifestly works. Your brain is incredibly complex, but somehow it's coherent enough for you to be able to listen to me speaking to you at the moment. So we already see with the human body that complex things can have at least vaguely predictable behavior. Okay, so here's the big question I'm going to ask. Should we give up now, or can scientists, mathematicians, that's what I am, or engineers, make any sense of all this complexity that we see around us, and can we use the knowledge that we might get from this to our advantage? So kind of this is the thrust of my talk. It's also very much what we're trying to achieve in Bath, and I should say there's many other institutions around the world, for example the Santa Fe Institute, that are asking very, very similar questions. Okay, so that's what we're going to try and do, and let's start with what people used to do. This is a kind of traditional view, a view which was widely held until relatively recently. The view was that nature is complicated. We look around and things look complicated, and the reason things are complicated is there's lots of things going on, and they're all independent of one another, and they just do what they do. Okay, that's a very kind of traditional view of what I will call a complicated system. So let's look at it as a really nice example of this. A really nice example, very British example, and you'll see why in a minute. The tides. Now, what causes the tides? That's a picture, by the way, of the sea just outside Bombay in India. Anyone who's been to Bombay might recognize it, or maybe not. Now, what goes on with the tides? What causes the tides are the motion of the moon and the motion of the sun, and those two interacting with the rotation of the Earth. Okay, so that's what causes the tides. Now, the motion of the Earth, the motion of the moon, and the motion of the sun aren't really quite in sync with each other, and there's various things which also add up to affect the tides. And the result is that the tides actually are a lot more complicated than simply going in and out twice a day. And here is a picture of the variation in the tides. This is the height of the tide in Bombay. So that's plotted. This was in 1872, so it was before computers were plotting things, hence the slightly rough nature of the graphics, over some several days. And you can see that there's quite a lot of variation in the tides. Now, why is this a particularly British thing? Well, in the 19th century, of course, Britannia ruled the waves, and also Britain was in the process of colonizing India. And they got to Bombay, and they wanted to have a port there, but they didn't know what the tides were. And the British Navy needed to be able to predict the tides some years into the future. Now, in the UK, you can predict the tides by just looking, I don't know, over the last 50 years. The tides pretty well repeat each other every 19 years, so you can use 19 years' worth of data to predict the tides into the future. In Bombay, they didn't have this information. They just had to do with what they had, the tides over a year or two, not very much more than that. So they had to do something, and this chap came along. Now, this is Kelvin. Kelvin is one of the greatest of the 19th century physicists, and he did an enormous amount of very important things. One of his principal inventions was he invented the telegraph, which is kind of important. So that's Kelvin. And Kelvin said, oh, well, the tides, they're pretty complicated. Let's think what we can do about that. And he decided that the tides were complicated because there were lots of things all combining to make them up. And for reasons I'm never quite clear on, he decided there were 37 different things which went to add up to make the tides. So that's what Kelvin discovered, well, or thought of. And he came up with the following formula. I will have a few formulae in this talk. This is a maths talk, but I will warn you as they come up. So that's his formula. The height of the tides, h, was the sum of 37 different periodic functions. That was Kelvin's prediction. And you'll notice that there are lots of things. 37 is quite a big number when you have to add these things up, if any of you have tried to add them up. There are these numbers aj, and these are numbers, the coefficients, which are things that you can work out by taking data. If you take a small amount of data, you can find what these numbers are. And once you've found out what those numbers are, then you can add all this up, and you get a formula which you can use to predict the tides. This is what Kelvin did. Now, Kelvin tried to add this lot up, and he kind of ran out of steam very quickly. He then subcontracted the job to his students, and they tried to add it up, and they ran out of steam pretty quickly as well. So he did something rather remarkable. He designed a computer to add them up for him. Now, some of you may have been led to believe that computers were invented after the war, or maybe during the war. That's the Second World War. But in fact, Kelvin can be justly credited with inventing at least one of the first analog computers. An analog computer is something which adds this lot up by machinery rather than by kind of electronics. And here's Kelvin's computer. It's rather wonderful. What it's got is basically 37 cogwheels, and each cogwheel goes round in a way prescribed by that formula, and then there's a wire which runs over each of the cogwheels, and the length of the wire is determined by what the cogwheels are doing, and the wire ends up adding up all those things, and as you turn the handle here, so the tides come out on here. And that's Kelvin's tidal predictor. So he invented that. Now, Kelvin was, of course, a Scot, and the Americans, of course, I'm here, have to pay homage to the Americans, decided to do better. So that's the American tidal predictor. As you can see, much bigger and grander. That was used to predict the tides with this same idea that you think of the tides as being made up of lots of independent things all banging on together. I can't remember how many there are. There's probably about 100 or so cogwheels in that. And that was used very well until relatively recently. About 1960, that was used till. So it's pretty good. Pretty good. So let's see what the tides are again. So what's happening in the tides is we do get complicated behavior, but that complicated behavior is arising because we've got lots of things going on. These things all combine together just by adding up, and what we see is what we call a resultant property of the combination of lots of independent things adding up. Now, that is actually not in any way the same as lots of the systems that I've been telling you about up to now. Many examples of complexity in nature are not like this. They're not caused by lots of things independently not affecting each other, just adding up. They are caused by things closely interacting with each other. And in order to demonstrate this, I've brought a demonstration along, and that's this thing here. Now, what this is a double pendulum. A double pendulum is very like my leg, or your leg. Imagine, well, you don't have to imagine, you can see, here's my leg, there's my knee, and my bottom part of my leg swings like that, and my top part of my leg swings like that. Okay, so I've got this sort of motion. And here's the double pendulum, that's the top part of my leg swinging like that, and that's the bottom part swinging like that. Okay, I hope you can all see that at the back. So that's the double pendulum. Pendulums have been around for years and years and years. Galileo studied them in around about 1600 and nearly got executed as a result. Anyway, that's another story. Great guy Galileo. He and I share the same birthday, a fact of which I'm very proud. Not the same year. Anyway, so pendulums, as we know, swing from side to side like that. Okay, you can find them in clocks. Their regularity means that you can tell the time using a pendulum. Okay, so that's nice, simple, predictable, understandable behavior. But it's not quite as simple as that. I can do this, okay, still going from side to side, doing kind of nice things, but different from the last one that we looked at. But that's not the whole story at all. In here we have a strong coupling. Here's my first component, that bit swinging like that. There's the other bit swinging like that. But these two are coupled together. They're coupled together through this joint here. And now let's see what the effect of that coupling is. Now that's a bit different, isn't it? Okay, this is what we call chaotic behavior. It's much, much more complex in what it does than the pendulum did originally. It's fun, isn't it? I can say that this very pendulum has appeared on TV. The Royal Institution showed it over TV as part of their Christmas lecture series. As seen on TV. Let's try it again and see whether we can work out what it's going to do. There we go. This, in a small way, is what the weather does in a big way. And this is a chaotic pendulum. So let's see what it's doing. The motion can be periodic in phase. That's when it's just swinging to and fro like that. It can be periodic and out of phase, where it's doing what it was doing. Those are both predictable. But this isn't predictable. This is what we call chaotic behavior. That's unpredictable behavior, but coming from a relatively simple system. Okay, all there is in this are two components, but what's important is that those components are coupled together. They're coupled together. So, scientifically, we can say quite a lot about this. Newton's laws apply to it. If I let θ1 be the angle of the top part, θ2 the angle of the second bit, brace yourself, there's a formula coming up, there we go. That's the equation for it. I know it looks ghastly. It's not quite as ghastly as it could be, because you can program this into a computer quite easily, really very easily. It's an exercise I give to my students in Bath, and you program it in, and the computer will produce a movie, and the movie actually looks just like that. Okay. So we'll move swiftly on. What's happening in here with a double pendulum is that it's made up of two parts. That part, we understand that motion. Galileo understood that motion in 1600. The top part, we understand that motion. Galileo understood that motion in 1600. But it's when you combine them, the coupling, we get a new type of behavior. And that behavior is emerging, it's emerging out of the interaction of the two parts in this complex way. Okay. So emergent behavior is what I'm interested in, and there's lots and lots of different types of behavior which emerges out of complexity. This is just one example, and we're going to have a look at some more now. Here is the aircraft undercarriage that I spoke about earlier, and what's happening in this aircraft undercarriage is a bit worrying. The aeroplane has landed on the runway, and there's an interaction between the tyres, which deform, the aeroplane moving along, and the runway itself, and rather worryingly, we get this effect. This is called shimmying, where the undercarriage moves in a rather similar way to this thing here. Okay. Not all aeroplanes do this, fortunately, but it's something we do need to worry about. Another example of chaotic behavior are the asteroids. If you take the motion of the Earth or the Jupiter or something, that's quite easy to predict. But the asteroids, which are coupled in strongly with the planets, can often move in a much more erratic way, rather like this pendulum. And one of the consequences of the fact that asteroids move in an erratic way is that occasionally asteroids can hit us. 65 million years ago, one's supposed to wipe out the dinosaurs. Who knows if one's going to wipe us out? We can't predict it. That's a bit tricky. Okay, so what do I mean by emergence? And this is something I'm going to kind of talk about a lot now. We've seen all these sort of complex things, and emergence is a property of something which is complex, which is much more than the sum of the parts. It's much more than taking all the individual motions and adding them up. It's much more than what Kelvin did for the tides. An emergence arises in complex problems from the way that the things interact with each other and not from just what they do on their own. Okay. And that's exactly what we're seeing in this pendulum. And one of the nice things about complexity is that if you look around you, you see lots and lots of examples of emergence, and some of which we understand and some of which we don't. As a mathematician, I'm very pleased that we don't understand some of them, because that keeps me in a job. Okay. And of course, it's nice not to understand things, because that gives you a challenge. So one of the nice things about emergence, and something I shall show you, is that even if you have something very, very complex, if properties emerge from that, then those properties can then be used to make predictions and even new designs. So let's look at some emergent properties. One is coherent patterns. So even if things are behaving complicatedly on a small scale, you might see sums of coherence on a large scale. And we'll look at some examples of this in a minute. Another thing which is rather more technical, but I'll talk about in a little bit more detail, are scaling laws, laws relating things happening on small scales to large scales. And thirdly, large-scale behavior, which is quite understandable. One of the things about climate is, although the weather is very hard to predict on a weekly basis, the overall patterns in the weather are relatively easy to predict. We know it's going to be cold in the winter. Okay, we know it's going to be hot in the summer most of the time. So often you do get long-scale things which are easier to understand than short-scale. So let's look at some coherent patterns. So, as I said, even if you have lots of things interacting independently, the coupling can often give you large-scale behavior, which is easier to understand. And flocking is a lovely example of this. If you've ever seen a flock, although the starlings, or whatever the birds are, interact locally through small-scale interactions, the flock can often appear to behave almost like one big organism. Another example which mathematicians study quite a lot is slime. Now what happens in slime is that slime decides it wants to clump together. So one bit of slime emits a chemical, and that chemical floats out into the sort of system. And if another bit of slime senses that chemical, it can move towards where it thinks the chemical is strongest. And that's a way of attracting. If you suppose if you put on a nice perfume and that perfume wafts away and someone might be attracted to that perfume, you might get people flocking together for that result. And what's wonderful is, although slime is really rather small, you get these very, very coherent patterns emerging because of the interaction of these chemicals and the slime bits. Here's another beautiful example which was discovered by chemists. This is called the Belousov-Zhabotinsky reaction. And in this reaction, you have lots of chemicals which react together and diffuse. And although chemicals are molecules buzzing around in all sorts of random ways, we get these beautiful patterns which emerge out of that. Okay, and these patterns are things which mathematicians can study. There's lots of very nice geometry in these patterns. I think any of you can see that you've got geometry here. And mathematicians can then go on and describe this geometry using differential equations. Now, when I was talking about examples of complexity, I mentioned rocks. And again, rocks are something I've been very interested in for a very long time. I naively believed that rocks, when you compress them, went into nice sort of wiggly patterns like that, and that belief lasted as long as actually looking at some real rocks. And these are our Cornwall rocks, and mathematicians in the audience, you might like to see these ones. Here we have an example of a rock which is nice and smooth there, and yet when the rocks combine together, these are multi-layered rocks, when you compress them, they interact with each other very strongly, and you get a nice singularity forming there. Okay, and this is all because of the way the rocks interact with each other. Here's a lovely pattern here. This is a lovely zigzag pattern. If anybody says maths is of no possible use, it never occurs in nature, have a look at that. Isn't that a nice bit of maths, that angle there? And that is caused by the fact that the rocks are interacting with each other. The layers interact with each other. You can't get nice sinusoidal folding patterns. They simply don't exist. And you're much more likely to get these sharp corners here. And this is in Cornwall. And for the geometers in the audience, that's the singularity that you get. It's an example of a swallowtail. And here's one of my favourite examples. I'm sure this didn't come out very well, but this is a picture here of a crowd of undergraduates. You can see, well, they've just graduated. They've got their hats on. Maybe you can see that. And I want you to imagine we've got a crowd that's walking in that direction. Okay? They decide to walk in that direction. Maybe there's some sort of football match over here. And then there's another crowd. Here's our other crowd. And it decides to walk in that direction. Now, each of these crowds is relatively random. Okay, there's all sorts of randomness there. And I want you to imagine you have two random crowds that are moving towards each other. And let's see what happens. And this is I'm going to show you a calculation which was done by some of my colleagues at Bath, looking at they're working on design of buildings and need to design buildings which people can evacuate from, and so they need to understand how the crowds behave in those. So let's have a look at them. So here are my two crowds. They're about to meet each other. They've just met each other. And what's happening here is the crowds have a strong preference for moving in their two different directions. So this crowd here wants to move that way. That crowd there moves that way. But when the crowds actually meet, they don't like each other very much, and they decide to bounce off each other. Okay, so as the two people meet, they say, oh, I don't like you, and bounce off each other. So you can see them bouncing off each other here. So they're random here, they're random here, they're interacting quite strongly over here. And what fascinates me about this is that you suddenly see some emergent patterns coming here. If you look, you can see we're developing stripes. This is much, much more organized than this. And this is a pattern which is emerging from the way these two crowds are interacting. And this fascinates me, that we get these strong patterns emerging, and you get quite a well-defined separation between them. Quite a well-defined separation. And this is very useful. It means if you're trying to design a building which you can, predict how people are going to behave in large numbers, this sort of pattern is something you can start to work with. This has actually been observed in real crowd situations, and this sort of patterning here. I'm not saying that crowds really hit each other like that, or ever. This is just a mathematical sort of play, but this is a very nice example of patterns emerging in crowds. Okay. So, let's shut that one down. Back to here. No, it's not going to work, is it? No. I'll just whiz it through. I'll do it the traditional way. No, it's very quick. You should be taking notes at this point. This is not my computer. Nearly there. Yes. Okay. So we've seen how patterns can emerge, and what I want to talk now is how we get what we call scaling laws. That's laws which sort of relate different scales in space, different scales in time. I apologise for the fact this bit's going to be a little bit more technical than the last bits. But one of the things I'm very interested in is understanding complex materials. This is a very complex material. This is a ceramic material, which that's 10 micrometers, that distance there, which is made by combining aluminium oxide and titanium oxide. And the reason we're interested in this material is that near airports, you have lots of buildings, people live near airports, or at least they do in England, and those buildings affect radar. They scatter the radar. And what they want to do is find a magic paint that you can paint on all the buildings, and that paint has the effect of absorbing the radar so that the buildings don't scatter the radar, and you can see the aeroplanes coming in more carefully, more easily. So this is a material they want to put onto buildings to be an absorbent electrical material. And it's rather complicated. As you can see, we have this complexity which looks rather like those rocks that I told you about earlier, where there's lots of variation on small scales, and things are all kind of rather higgledy-piggledy. These black holes are the holes, they are physical holes in the material. Now, when we look at this mathematically, the titanium oxide, that's white, looks rather like a resistor, and the aluminium oxide, that's grey, looks rather like a capacitor. And so we can try to understand things like this in terms of mixtures of capacitors and resistors. Now, when you take such a material, one thing you want to know is how the electrical properties vary according to the frequency of the signal that you apply to them. That's rather important in our understanding of how they behave. And this was a plot that we did. We took lots of different materials. So we got the manufacturers to send us lots of different materials. And for each of those materials, we plotted a graph of the frequency on the top against the conductivity here. And each of these lines represents a different material. And this is what we found rather extraordinary. Over here, for low frequencies, there was a wide variation in the properties. It was all kind of random. For high frequencies, again, there was a lot of randomness. But in the middle, everything seemed to line up and have some sort of emergent behavior. There was some sort of predictability in the reason over there. Now, we didn't understand this initially, and so what we did was do some simulations, mathematical simulations, of what we thought was going on. So we built kind of mathematical models of these materials. And this is what we found. So what I'm drawing on the left, this is a picture of the way that essentially the conductivity of the material. So what we're seeing there is basically paths taken by the electrical flow through the material. And on the left, we get a preponderance of resistance and all sort of vague sort of lines over there. Nothing very helpful. Over there, still rather vague. But when the thing starts to get predictable, everything starts to kind of merge together. We're starting to see this strong coupling that I told you about was important in understanding the sort of complexity that we want to see. And there's strong coupling there, but for very high frequencies, the coupling breaks down. So the emergence here is definitely a property of the way things are coupled together. Now, mathematically, what's going on is this. Here's our frequency, conductivity plot. The random bits are what we call percolation. This is where things wander around and don't have very clear paths. But in the middle, where everything is interacting and working well together, we get this emergent region, and that emergent region has a well-defined law explaining what's going on, and that law is great because we can then go back to the manufacturers of the material and say, in this region, we know what's going on. Okay, I don't know about that, I don't know about that, but if you operate it over here, I can tell you what's going to go on. And that's because these properties are emerging out of kind of the mists of this material. Now, the sort of law that we're getting here, and apologies to the audience on this one, is that the conductivity is proportional to the frequency to a power law. This is what we mean by a scaling law. And this, again, was a very great surprise to us that it was as simple as this, and the power law in this case was 2/5. We vaguely understand why now. So this is an example of what we call a scaling law, which emerges out of a complex system. So with apologies to those of you who know all about this, what do we mean by a scaling law? Well, basically, that there is something which we can measure, let's call that A, something which changes, which is B. For our material, we can measure the frequency, we can measure the conductivity, we change the frequency, and they are related by an equation which takes the form that this number A is some constant C, which is something you can measure, times B to some power gamma. And again, gamma is often something you can even work out. And what's amazing is that laws like this arise all the time in incredibly complicated things. Things where you would have thought there was no possibility of any law coming out, and yet these sort of things seem to pop out of nowhere. And these sort of things lie at the heart of a lot of the way that we can try to explain how things go on. So I'm going to give you a rather interesting example of this, which led to a battle between the US and the UK. Okay, so I thought a little local colour there. And this was all about a rather fearsome thing, namely the H-bomb. Now, I'm not suggesting that the US dropped an H-bomb on the UK, or even vice versa. Let's hope it never happens. But let's tell you the story about this. This is the hydrogen bomb, and the first hydrogen bomb was exploded at the Bikini Atoll in the 1950s by the US, US Air Force, I suppose, or whatever. And they were very proud. You were very proud of this achievement. Well, some of you were. And a film was released of the explosion. There it is. And looking at the cloud. And that film was shown on British cinemas. Okay, this was, by the way, before I was born, in case any of you wondered. And we can see here what the film shows is the cloud growing. Now, what's happening in an H-bomb explosion is very complex. You have a detonation, lots of things happen. That heats up the air, lots of things happen there, and you've got this then sort of fireball which emerges out of that. Now, in my previous example, I said one of the features that you often get from even very complex things is a relationship between one quantity that you know about, another quantity that you can measure, and there's some power law which relates the two together. And in this system, you can measure the radius of the fireball. Even on the film, all you had to do is take the film and, well, you know how big things are. You can measure the radius. Another thing that's affecting things is obviously the energy of the bomb. And another thing that affects things is the time after the explosion. So all sorts of things can happen, but what emerges out of all of this is a law which relates all of them together, a scaling law. And the scaling law, in this case, is that the radius is proportional to a constant times the energy of the bomb to the power 1/5 times the time to the 2/5. Now, the person that worked this out was a guy called G.I. Taylor. G.I. Taylor was at the time professor of mathematics at Cambridge University. In my introduction, Professor Arnold said that I got my doctorate at Oxford, but I also got my first degree at Cambridge. So I never know who to support in the boat race. Anyway, G.I. Taylor, he was professor of maths in Cambridge, and he came up with this formula, and he managed to calculate this number C by doing some experiments. Because this formula doesn't matter if it's an atom bomb or a small explosion, he did some small explosions and worked out what C was in the lab. And once he'd worked out what that was, by looking at the way that the atom bomb in the film grew, the H bomb in the film grew with time, he could work out the energy of the bomb. So very proudly, he wrote a paper and wrote down the energy of the bomb and said the atom, the H bomb, had the following energy. And this was the cause then of the difficulty between the US and the UK, because of course the energy of the bomb was a classified secret. And this led to a major row, but as G.I. Taylor said, well, the energy might be a classified secret, but the film isn't. Okay. And so he got away with it, and his value was about right. And it was all because he recognized the importance of scaling laws which emerge out of complex problems. Now, there's lots of other examples of scaling laws. A rather remarkable example is the Internet. The Internet is a very complex system. Computers are coupled to computers are coupled to computers. And people have done a lot of studies of it. By the way, one of the most important applications of maths that there is the Internet. And some of the richest mathematicians around are the people that founded Google. So if you ever wondered what's the importance of maths, you just say the Internet, and by the way, you can earn lots of money. But people have studied in the Internet things like how many computers are connected to, if I have a computer, how many computers do I connect to with the Internet? And they have found scaling laws relating the number of computers that my computer connects to and the likelihood of that happening. And these things are useful in studying how to do things on the Internet. Networks of friends, social networks, also exhibit scaling laws, and you can work out quite a lot from that. And that, again, is rather remarkable. Disease exhibits these things. Mechanical systems, here's a very kind of complex bridge-like structure, but the forces in that obey these sort of laws. Interactions of proteins and genes behave these, and also things like rocks. When I started the talk, the first example I told you about was that rather complicated pattern of rocks under the ground. But if you actually have a careful look at it, you find that scaling laws emerge from this, which relate things like the pressure of the water on the rock to the way the water flows through the rock. And why is that important? It's important because you can build that into computer codes describing this very complex behavior, and those scaling laws then tell you how the pollutants flow through the rock, and then that's very helpful in understanding the long-term behavior of pollution flow, or and it can be very long-term. One of the problems that we're faced with is what to do with radioactive waste, and understanding pollution flow over hundreds of years is necessary to dispose of radioactive waste safely. Move through that one. So I want to conclude my talk now by saying how all of these sort of ideas that I've described sort of come together in looking at a very important problem, namely forecasting the weather. So the atmosphere interacting with the ocean, which is the driving force behind the weather, is very, very complex. There are many, many length scales. There are many, many time scales. And yet the weather isn't something that we can ignore. It's something that we do have to study and make predictions for. Obviously, we need to know what the weather's doing. I need to know what it's going to do on Sunday because I'm flying home on Sunday and I'd like to fly, you know, relatively safely. I want to know if I'm going to get the plane or not. So we need to make predictions. But what gets in the way of these predictions? Well, one is the weather can do lots and lots of different complicated things. And although we've got satellites looking down on the weather from space, there's nowhere near enough satellites to capture all the things the weather can do. Secondly, we know that the small-scale behavior can be very chaotic. There's our picture that we looked at earlier from Leonardo da Vinci. Thirdly, within weather, there's lots of things on the small scale that affect the large scale. And turbulent behaving fluids, we see energy moving between large and small scales all the time. Lots of random events. There's a famous quote by Lorentz, the meteorologist, that the flapping of a butterfly's wings in the Caribbean could cause a storm in Africa or something. Well, we now know the butterfly would have to have rather big wings for that to happen, but it's still true that there's lots of random effects which obviously do affect the weather. And thirdly, finally, the computations are very, very hard. This is a picture of the supercomputer that the UK Met Office has, and some of the toughest computations that we have to make are those which are used to forecast the weather. Okay, it wasn't until relatively recently that we had computers powerful enough so that the computer predictions of tomorrow's weather could be done in under 24 hours. Okay, and it's a bit pointless taking 2 days to compute tomorrow's weather. Okay, so very, very big computations. So there's all these things which are effects of the complexity. But we can start to make inroads into this using these sort of ideas that I've been describing. So one thing is these famous scaling laws I've been telling you about. What scaling laws do is they do tell you how small scales and large scales interact with each other and how things, let's say, if you know what the weather is like close to the Earth's surface, what it's going to do higher up, and that's very important. And building that into your computer codes markedly speeds up the computations. I mean really does. It can make a difference of many, many orders, a million times faster by using that amount of maths. Secondly, although the weather is very complex, you do get large-scale patterns emerging. And the way we use satellite data is we take the data from the satellites and we say what patterns of weather, what expected patterns of weather best fit that data, and then once you've got that, then you can use that to inform your weather forecast and also, and even more importantly, continue to compare your weather forecast against the data. And these sort of ideas are vital, and they use all the sort of techniques that I've described to you in this talk. The fancy word that the Met Office people use is data assimilation. They also use other fancy words like that. I put those in because my friends in Bath work in this and they've asked me to tell you about them. But the point of the matter is that we do, by trying to understand more about the way complex things happen, about these scaling laws, about the way you get these patterns, you can build this into forecasting, and it really does make a difference. So I've taken you on a kind of whistle-stop tour through all the complexity that we see in nature and the various things that can happen. But just to say, there's lots of other examples around where we understand that these things are happening, but we don't understand enough to make as many predictions as we want. Spread of disease is one. Behavior of customers in large retail networks. People are actively trying to use these sort of ideas to understand that. Transport networks and chemical reactions are all other examples of systems which have the same sort of behavior, but we don't really understand it. And just to finish with saying there's much still to be discovered, and those of you who are a lot younger than me in the audience, I'm sure these are areas that you might end up working with and making big discoveries in. And I will finish that.
thank you very much for a very, very stimulating lecture. We'll take a couple of questions. Before we do, I just had a couple of short announcements. For students who need a certificate of attendance, we have them down here at the table. There's also left a few souvenir postcards, if you would like one of those, and the poster of upcoming lectures. The next lecture is going to be on March 7th. It's about pattern formation and symmetry. It's called Patterns Everywhere by Martin Golubitsky, who's a well-known mathematician and also the author of a popular book known as called Fearful Symmetry. And so you can pick those things up here if you're interested. Are there any questions for Professor Budd? Emergence,
yeah, it's where you get kind of properties that, although things are kind of interacting in a kind of random way, the effect of the coupling between them means that you get these kind of larger scale, much more coherent structures coming out of it. So things which are arising not from the individual motions, but from the way things are interacting with each other. I wish I could say much more than that. I mean, there's how patterns emerge and what things emerge are things that we're actively trying to understand in research at the moment. Yeah.
When patterns emerge out of randomness, it would appear that there is a decrease in entropy. So is there a physical explanation of that coupling that should explain this?
Repeat the question, Chris.
He says that there's a decrease in entropy. The general answer I will give you is that you get a local decrease in entropy, but other parts of the system still remain disordered, is the best way I can explain that. But, I mean, you very often do see kind of structure emerging from randomness, and it's essentially localized, or there's some input into the system which is putting energy in, which is allowing this to happen.
Is there another question? Okay, well, thank you very much for coming. I hope to see you again March 7th. Thank you.